Okay, so we continue. I think this morning is really nice in the program. You know, we had one talk on quantum circuits, advanced math techniques to master them. Now we have a talk on actually experimental advanced techniques to actually learn from them and see what they give us. So please, Pedram, take it away.
Yeah. Yeah, thank you. Thanks for the invitation. It's been a great conference so far. I want to present some of our recent experimental works. They are a bit uncorrelated from first part of the talk to the second part of the talk. They're just maybe a sample of NISQ experiments that we do. Yeah, there was one more thing. So let's just start with this first part, which is about measurement-induced phases of matter. For many years, we have been maybe a little not paying close attention to the problem of measurement, or we were focusing on things related to unitary evolution. And well, it's partially into quantum mechanics, which gives you a dichotomic view. One is that if you don't watch and observe a system, it evolves under Schrödinger equation. But if you start looking at it and watch it, it would go and would do collapses to one of the eigen values of the local observable or observable that you have chose to measure. So the question is what are the possible phases of matter that could emerge when you are mixing these two things? Like, show it one more time if it plays for me. It was not a good idea. What are the possible phases of matter could emerge when you mix these two things together? Meaning that you have measurements and you have the unitary evolution at the same time. This question becoming more and more visible, or more becoming to focus as error correction and whatnot brings this to our attention. So many people who have been historically and traditionally consider themselves as quantum statistical mechanics and non-equilibrium dynamics now start to thinking that what are the possible phases that could emerge if you start merging and mixing. And the interesting question is, what is that even possible to have phases of matter of quantum information? That is impossible to do otherwise. So with that, I can introduce the circuit that we want to analyze in this case. Consider a circuit that is a mixture of unitary evolution. The blue icons are the unitary evolution, and the yellow ones are measurement icons. So instead of having all the measurements piled up toward the end of the circuit, now you're saying I'm going to remove some of the unitary operators, and I'm going to put a measurement in the middle of the circuit. Okay, so we're going to start a 1D problem, and we're going to gradually build up to do with more sophisticated version of it. And then we ask after some time, what is the structure of the or what is the structure of the wave function of the system? What are we going to get in this circuit? And that's a question we are going to ask. There has been focus of attention, as I said, maybe some from error correction community and some from traditional theoretical physics, people who like to think about it as a phase of matter. But it's, yeah, sure. So yeah, that's what I remember. You should ask question during the talk.
In the circuit, are you feeding back the measurement values into the circuit or not yet?
No. I get to the challenge. We don't do it yet. What is the good thing about to do it with a quantum processor is that you can really see how susceptible or what's to noise is these kind of circuits. Something that would be extremely difficult or impractical to do on a theoretical study. There's lots of theory study of these models, but to understand how noise affect these things, and I have some news at the end of this part, we need to do it on the quantum circuit. So of course the work is done by not me, by this group of people in collaboration with our colleagues at Stanford University. The work is published maybe a year or two ago. So let's consider two quantum states, not that generally to get the discussion going, not that we are going to go with these two particular ones. Let's consider the highly entangled states, and these wiggly gray lines meant to show entanglement. Every qubit is highly entangled with another qubit. So if you really trace out a subgroup of qubits, you have to cut many lines. But you can also consider another scenario, let's say in a many-body localized phase, where every qubit has a very local entanglement, which is near neighbor. So when you're cutting it, when you're go looking at a subgroup of qubits, the entanglement is cardinal proportional to the area of it, not to the volume of it. Okay. So what happens to these states when there is an entanglement gate, and what happens when there is a measurement? The gates that we are considering are propagating entanglement locally, meaning that they stick two qubits together, but the measurements are non-local, meaning that they purify a qubit, they collapse the wave function locally with a very, that qubit could have been connected to many other qubits. This simple observation led people to conclude that when you go large on the thermodynamic limit, there would be any finite number of measurements, any non-zero number of measurements, because of its long-range effect, would dominate. Therefore, as soon as you start to replace any value of unitary evolution with measurements, there would be a collapse of the volume law phase, or the measurement would take over. It turned out not to be the case. Later on, three independent researchers, research groups, understood that if P being the percentage of the unitary gates that you replace with measurement, this PC can be non-zero. The original study was that OPC is always zero as soon as you enter to an area law phase. But then they realized that they figure out that the quantum information in the volume law is so subtly hidden that measurements can survive up to finite percentage of the measurement. So they proposed that it would be a phase transition, and the phase transition happens at a finite value of PC. So these are some of the theoretical early works, and we are inspired to do the work. Okay, so now get to this question of what do we do with this outcome of the measurements that we do? Well, the most trivial thing is that you bookkeeping what the outcome of the measurement is, and then you repeat the circuit. The outcome of the measurement is going to be different. If you start mixing these things, you get a mixed state, and then as this line of algebra would show you, you're only going to get things that are linear in the density matrix of the system. So you're going to get only boring properties. So you should not mix measurement outcome which are distinct from each other. Meaning that if you choose to measure 5 qubits or 5 places, you have 32 possible outcomes, but then you have to repeat the experiment and look for those outcome cases that show you exactly the same one, and then bundle those together and work with them together, and don't mix them up. If you mix them up, you get nowhere, or you get very, very limited number of questions, particularly when we are interested in entanglement entropy, which is nonlinear in the density matrix, would not come if you average over distinct measurement outcomes. Okay, that's one challenge. They call it post-selection challenge. So meaning that we have 10 qubits, choose to put your measurement in 10 different places, then you have really 1 out of 1,000 bit string that you got to keep looking for. There is another problem that is just dear to me and Derek probably, is that's in real life. In our circuits, the measurement is slow, meaning that it's just about 20 times more than the gate, at least in our graph. Meaning that you got to entertain the qubits, and they will dephase and decohere during when you're trying to go. The cycles become very, very long. So you could do dynamical decoupling and whatnot, but it still is very, very undesired to do. In this work that we have published, I'm claiming that we can show that how to address these questions and how to partially solve these issues that I'm raising. Okay, so at Google, we heavily rely on oracles. We don't have any specific agenda. We just watch YouTube commercials tell us what to do. In this case was that use a space-time duality. Okay, so I'm going to explain to you how a space-time duality picture could help you to get over this post-selection and measurement problem to some extent. And then, of course, the big problem to solve it for general remains open problem, and we don't have any answer to that. Well, let me explain the idea. The idea can be said very simply, which is you kind of swap, I think it was brought up in maybe first day of the conference or something, that you swap the input and output, or rather you tilt your head. What is called a space, you call it time. What is called time, you call it a space. So you look at these units as a tensor network, and then there's input and output, but then you kind of mix input and output by kind of rotating your head 90 degrees. And that could be, in fact, useful in certain cases. So there would be a mapping that we will show you, that this problem that we like to solve would be mapped to a 2 plus 1D problem, meaning that you have an XY plane of gaze and you repeat it, but the benefit of it that now all the yellow measurements now are piled up at the end. So now the measurement has moved through the middle of the circuit. They have kind of diffused to the surface of the circuit. They're all piling up at the end. So that's a advantageous, but then we see how far we can go with that. And the original or the thinking behind it is that you usually think about causality and you think about the arrow of time in a unitary circuit, and but as soon as you turn your head, the unitaries turns into Hermitian operators, and it's not very pleasant. But here, by introducing measurements and doing partial collapse here and there, you're just you don't have the notion of light going as simply as you might imagine, anyways, to begin. So it could be beneficial to do that. So let's solve a contrived problem, and then we get more serious and we solve something maybe more interesting. In this contrived problem, let's suppose that someone asks you, what is the entanglement structure at the end of 7 layers of qubit operations in a chain of 12 qubits? The operations are a mixture of unitary and measurement. Rather than having unitary some places taken out, replaced with measurement, we come with a gate, which is a mixture of unitary and measurement, and we spread it uniformly across. Okay, so what the good thing is that we knew that if you do dual space mapping, as I mentioned, the dual space-time mapping of this object would be unitary. Okay, so in this case that I contrived, we know that this is a unitary gate, and then the space-time duality of it is this one, which is not unitary anymore. But I ask you to ask me what's the answer to this, then I go back to this. Okay, so it's a bit contrived, but I'm trying to show the power of the method. That in this case that I can work out the math for you. If the question was this, the answer is this. This is space-time mapping that goes both ways. Okay, so please ask us this question. And if you ask that, then what we would do, we would replace space and time. And then you see the problem, which was stretched over 12 qubits, now stretched over 12 steps in time. And the what was 6 or 7 steps in time now become stretched over 7 qubits. So these two problems are identical to each other. You can choose to solve whatever you like. Okay, the B is slightly better, but now it has the thing that we were interested in, the wave function that we're interested in, is properties. Now is stretched over time over a single qubit. But that is solvable. The solution to that is something called a swap matrix. And you just introduce more qubits and you get that information of the wave function comes. So you add another 12 qubits to the system, and qubits are free, so you can have them. And then you arrive at problem C. So my point is that problem A and B and C are identical. There's just a mapping. And you got managed to figure out boundary condition and all that. So of course we chose to solve C. And when you do that, you can answer the original question that was posed about, let's say, the second order Rene entropy. the wave function that you're getting at the end of it. And you see signatures of volume law and area law. They're not exactly area law, I forgot the name, log area or something. But anyways, you see with the different choice of parameter, which is changing the ratio of unitary to measurement on that in that small unit that I showed in this object. You can, feel how much is blue, how much is yellow, and these two parameters sets that. And you can see two very distinct behavior after measurement of second order running entropy. Okay, that's good, that's encouraging. So what it tells us is that at the end of the day, 1D problems, even less contrived, can be mapped to 2D problems. So now I go to our 2D problems that we are very comfortable can implement, which is in this case of you have layers of gates in 2D and finish by and ending up by measurement. And I'm claiming that there is a circuit, 1D circuit, which is far more unintuitive again. It's a bit has long-range entanglement and whatnot. But if I solve this problem in 2D, it's the answer of what happens in this circuit. So we are going to be less specific on the problem. Well, I mean, we can be specific, but it's not intuitive to look at it. But the reason being that we want to answer the question of what happens essentially as you change the percentage of unitary to ratio of measurement. That's the key element that we would like to play in here. So again, we start with second order running entropy, and also mutual information defined this way with subsystems of A and B over that chain of qubits. And we can see that, if you increase the number of depth of the number of unitary layers you're doing, that's this T parameter, you see a sudden jump between as much as sudden can be as changing number of layers between something which entropy was kind of flattening out versus to something that shows a big jump to a volume law type of behavior that is called a page curve. Mutual information more or less talk about this, show you the same physics, and we get to analyze that more, give me a second. So we can do measure the function of distance. Distance between A and B is 2 qubit A, these 2 qubit B, they can be next to each other, 1, 2, 3 distance from each other, and you say what's the mutual information between them as a function of their separation and as a function of time. And you see there will be a time after which they are just having a very high mutual information together, they are entangled together in this sense, and irresponsive of the distance of the separation between them. So no matter where you go, you see a high mutual information between, regardless of the separation. Okay, good. So let's slow down a little and analyze this thing a little further. So now we are just going to keep looking at the mutual information. This is a line cut into a plot from the last slide. And this two color is just our suggestion. We don't have from our experiments, which says that a mutual information is 0 between these two qubits when they are at some separation 3, and then all of a sudden there is a jump to a state in which there's a large mutual information shifting. So focus on layer 3, the depth 3, 3 layers of unitaries, and then you see the mutual information falls down. It means that if they go further apart from each other, there will be no mutual information between them if the layers that you apply unitary is only 3. But if you go to 6 layers, regardless of their separation, there is a solid piece of mutual information between pieces. Good.
So is it like a light cone effect, or is it a smaller velocity that's...
It is light cone, but it's not to be confused with the unitary light cone and all that. You are getting entangled much sooner, and it is a phase transition, which is its own business, because of the measurement, much sooner than what you expect from the light cone hitting. But this is the same phenomenon in a sense, but not to be confused with the unitary. Unitary would be at cycle 8. This is more at cycle 2. Okay, so okay, something I saw under the rock was that there are measurements in here that pile up at the end, but you have to post-select in these yellow elements, yellow qubits, which are 12 of them. And so it's getting very challenging. 4,000-bit strings, you have to sort out. You have to maybe get 1 million or 10 billion measurements, and you have to not use most of them. So we have to get over this. So we are going to get the help of classical computers in a little more sophisticated algorithm, which is essentially coming from all these ideas of error decoding that is spoken in the error correction community. So essentially what we are going to ask is, if I choose a qubit as a probe qubit, how many qubits in the neighborhood I have to go to collect the information about this qubit? How much information about this qubit has propagated? And what is the vicinity or neighborhood that this qubit has been affected? So the algorithm is a bit complicated, and I usually fail to explain it properly. So let's just go do it very slowly. So you run a 2D circuit, and you choose to measure all the qubits at the end, and you feed this measurement to a classical computer. All these yellow measures, you tell the circuit to the classical computer, you tell all the outcome of the qubits, yellow qubits that have been measured. And as the classical computer, can it predict what would be the state of the magenta qubit? Is it up or is it down? Classical computer give you yes or no, or plus or minus answer, one binary answer. But you have measured that pink qubit yourself, and you compare them and you make a cross correlation between them. Okay, so that is the idea. And then you figure out what is the decoding radius, meaning how much of these measured qubits you have to fit to the classical computer to increase this correlation, or to increase the chances of classical processor to predict what happened at the magenta qubit. Is that clear? It's not intuitive by any means. So let me just say, so these measurements are fed to a classical computer called decoder, and asking, can you predict if the magenta qubit is up or down? It tells you tau m, and you put tau m next to ZP, which comes from your own measurement of the magenta qubit, and you form these correlators. Maybe it become more clear if I say that instead of this correlator, we can talk about this proxy of entanglement. This correlator with this simple functional form, I can talk about this proxy, and that's a little more intuitive thing as I make it clear for you. So let's just look at it again. What we are going to do, we are going to change the system size, and we are going to change the number of times, since now we are doing all the measurement at the end, and we don't want to discard any of the measurements, what we are going to do now, we are going to tune our unitary. The way we are tuned the unitary is to by replace some of the entangling gates with an identity gate, and that's where these white elements meant to represent. You meant to apply a unitary entangling gate, but there is a chance that you skip it. If you skip many of them, your entangling unitary becoming very weak. That's this rho close to zero limit. But if you don't skip any of them and you do them all most of the time, this rho become close to one, and you have a very dominant unitary, and that become, and then we see whenever what value of rho it overcomes the measurement. So there is Cassie and there is normalized Cassie. I get back to them later, but I said it makes more sense to look at this proxy for entanglement. And this decoding radius, let me repeat, is how much of these measurements is fed to the classical computer, and ask the question of, can you find the correlation and whatnot. When rho is 1, you see that this is very strong unitaries, and then for all system sizes that we look, to retrieve the information about the qubit, to see how far the qubit, you have to go pretty much across the entire grid. Maybe you didn't emphasize enough. The way this rho is defined is layer by layer, right? Decoding radius, layer by layer is added. You could have had it maybe circular, but whatever. This was simple enough. And it's only when you get to the end, of course, when you get to the end, you have to drop to zero, right? It's a pure system, so the information has to be somewhere into the system. There's well, we do a correction to it. I get back to it later. But when you get rho becomes 0.3, meaning that become a weak unitary, you see that the entanglement proxy, as it shows, it drops with distance. And after a few decoding radius, you kind of got all the information you want. You have all the prediction capability. Classical computer predicts what happened at the magenta qubit very precisely, and you don't need to go further out. Of course, the last point is always precisely 0. So it kind of now we get a hold of the entanglement structure in the system, and now we can go and, for instance, play with this value of rho, which is tuning the strength of the unitary as a function of decoding for this system size, for this depth. And you can see as I tune the strength of unitary, you can see a clear change in behavior from being spreading over to something which the concavity of it starts to show change in behavior. And you can ask the question of what is this proxy as a function of this density for with respect to well, by fixing the radius to the last one. And you can kind of probe the transition in this case. And you can see crossing as a function of system size, indicative that there is a transition, a phase transition, and our crossing point kind of points to the value of when this transition takes place. Is distinct, different from numerical prediction, and that is exactly tells you what happens in a noisy quantum system.
So,
yes,
is there a calculation type understanding of this transition? Calculation. I mean,
so in certain cases, the universality class and whatnot is known, and sometimes percolation for simple models work, but this is not the.
This is not. Let's see.
Yeah, percolation can explain some cases. It's maybe liquid cases or something. Yeah,
Not this case.
not this case. Yeah, sure.
Question. And understand the connection between this and lowering the post-selection overhead. Are you saying something like, if you can show that the probe qubit, the entanglement stops growing very quickly, then
No, okay, that's a good question. We did not lower the threshold. Yeah, that's a very good question. We did not lower the threshold of post-selection. We came up with this decoding, which took us very far. I think the answer, that's why I said partially we answered it, because look at these sizes. We are getting up to 70 qubits. And I showed you after 12 post-selection sites, we are out of breath. It's just 4,000 strings, and we just cannot handle it. But here you can really go and change this how many times you measure, because you're relying on a classical computer. So this method also has its limitation, but we kick the can down the road a little bit. Yeah, we did not solve the post-selection for general cases, but this decoding helps you do it slightly later. Okay, so promise I have news beyond what theorists would have told you before. And these are two interesting pieces of news in this. So the system is meant to be pure, means trace of rho square for the entire system must be 1, and is not when you do this measurement, and they fall down. They fall down, this number must be 1, as I said, it's just based on purity arguments. And you can use that to probe the system. And there are two very nice behavior we see. For instance, one is this one, which is every number you see here, theoretically, for a very good pure system should have been 1, but it drops. And that is we use to normalize what I'm saying. That's what we are against. So it shows something interesting, that the susceptibility, the dropping or the dephasing of the wave function, coupling to its environment, increases when it's highly more entangled states. So good many-body systems, good highly volume law systems, volume law states are more fragile, are more prone to environmental noise than more pure type of state, more area types, and that's what this curve is telling you. This is all meant to be 1, but they are not 1, and you see this is far more sensitive than the alpha. But also it tells you something interesting. Another thing interesting comes from, okay, I keep getting this number, measuring should be 1. It's not 1. I divide by this number, but how far I can go in terms of signal to noise ratio. And it tells you to an effective coherence volume of the system, which to this experiment, as this experiment's probe, is about 12 qubit by 12 qubit. It just becomes extremely impractical to divide by these numbers, which are getting smaller and smaller, and you get dominated by numbers. So in a simple language, unless we solve the coherence issue, making bigger chips is pointless. Okay, that's super simple language, and I'm very happy that we measure this number directly. So fixing of qubits is needed. Great, exactly 30 minutes. So now I can jump to a totally different talk, totally different subject, if you guys okay. Questions? Okay, so yes.
How is the coherent volume kind of calculated again?
Oh, it's just this number you see.
Yeah.
This number is a hand wavy. This number should be 1. System has to be pure. It's not. And then with this finger scales, and then you raise 0.97 to n, and if n is 144, it just takes 5 days to get 1 data. Something very impractical.
Yeah, it's not like 1/e or.
No, it's just no matter where you get your grad student from, you get into some labor law kind of conflict. That's
So in the previous slide, this transition point,
Yes.
for
Yes.
reduction, it
yes,
seems to shift to higher and higher gate density as you increase your system.
yes.
Does it converge to somewhere, or is there a way to know, or does it just go to?
I think yes. I think sadly would keep going up. Yes, that's all we got, and the theoretical value is slightly lower than here, and I think that's the indication that it's drifting, and it would be very complicated to analyze.
You mentioned that you don't do feed forward in this, but does this duality work if you also have feed forward? I guess the question is that can you do error correction just by deferring all measurements to the end?
I don't know. I think that in this context, they're not much into feed forward. I maybe rarely or never seen a paper on measurement induced phases. They keep saying post selection. If you are measuring it and you are not on the quantum trajectory branch you've got to be, fixing it is not something you want to do. I think in this context, they don't care about it. Yeah. Okay, so the second talk is on this subject, is on realizing topological states, and I try to connect it to our lattice gauge simulation that we posted on arXiv a few days ago. So this is a few years old. Most of these people lost him, all that kind of thing. So, but that's, yeah. So it's one collaboration with our friends at UM. That's it. And the story of realizing, simulating the ground state of the Kitaev model probably is not news to you. This is a Hamiltonian, solvable Hamiltonian is written to be solved, and then we just say that can we just make it, as a phase of matter is interesting for some topological quantum computation, but here without realizing a phase of matter, we don't go into zero temperature and whatnot, can we synthesize the ground state of the system? The system has, the Hamiltonian has 2 terms, all these terms commute with each other, and I'm defining them. And they are defined on a link of a square lattice, but since we are going to measure these observables, which are stabilizers of the code, we chose to just define the 45-degree tilted lattice. And then when we are in the ground state, when you realize the ground state, all AV and BP will be +1. And when they become -1, if you measure one of these AV over a vertex or BP over a plaquette, and when they become -1, we can interpret that as the presence of a magnetic charge or electric charge. This is just interpretation. You can switch which one is E, which one is M. But that's the essence of the model, which and then you can think of them as quasi-particles that you can braid them. This case would be Abelian and boring, but you can figure out the ways to make them even non-Abelian. So that's a simple model, solvable. And the beauty of being solvable is that the ground state of it can be written in a closed form, and that gives you a recipe or how to create the ground state of this system. And we managed to, with 6 layers of gate operations, every qubit got given to be on this state, and then after a couple of layers of C0 gates, you arrive at this state, which I'm showing you the value of its its stabilizer or our AV and BP measure. And again, the guiding line was that is in every textbook that the ground state can be written in this closed form. Is a sum of all possible gas loops, essentially. And that would lead to a very simple recipe, which is linear in a shorter dimension of the system. So we made the ground state and we measure stabilizers, and it's okay. Well, what is the telltale of the topological ordering? And that's the topological entanglement entropy. So to figure out this universal contribution to the topological entropy, you have to measure entropy of pieces, and you remove the edge effects from that measurement. That is why it's defined this way. You see, when you do S of A, you define 3 edges, and then you keep adding and stop subtracting the edge contributions, the perimeter contributions, and then at the end of this addition and summation, you would be left with something pure. For a non-topological, topologically trivial states, this number got to be 0. But in this case, it would be non-zero, as we are about to see. The guiding principle is that since it's an exactly solvable model, we know that the entanglement entropy of, let's say, these 4 qubits is given by this simple relation. And you just count this number of darker blue boxes that it crosses. So it's a very simple recipe you can have for it. And log of 2 is just to make peace between condensed matter and quantum information. You go, let's focus on this top row. This is, you go to the patches of 2 qubits. There are many of the groups of 2 qubits you can find. And you say, what's the entanglement entropy of group of 2 qubits, group of 1 qubit, group of 3, group of 4. And you measure its entanglement entropy, and I'm just showing you the histogram of all possible groups of 2 qubits I could do measurement of. And then here I come for this construct. I come up with, I measure the group of 2, group of 4, this shape and whatnot, this shape. I measure all these possible cases that I want, and I form a histogram of them in here. And then the answer is kind of boring up to 4 qubits, 3 qubits, sorry. Because, you know, you measure entanglement entropy of 3 qubits, the answer is all centered around 3. You measure 2 is all centered around 2. When you go to higher numbers of qubits, now you have the notion of interior, and that would lead to non-trivial values of entanglement entropy. And then you can say, okay, this 2 by 2 group, I have these 2 added up, A and B and C, and then subtracted, and then make the histogram of topological entanglement entropy for this configuration. And then here for the 2 by 3 configuration, and so on and so forth. And you see, in all cases, you end up with -1, which is what it should be.
Sorry, I have 2 questions. So, first of all, I wonder what's the geometry of the better. What's that? Is it on torus or
no? No, it's open. And then you can engineer the number of ground states you want to be unique by playing with the boundary engineer.
And how do you so how do you measure the entanglement entropy?
By measuring rho, trace of rho squared. So I make the density.
How do you trace?
No, I make the density matrix. I go to 2 qubit, I do all possible Paulis, and with max likelihood, I make a density matrix.
Right, okay, I see.
Okay, good question. This measurement is okay, up to 6 qubits, you can do tomography, but this guy, this object, 9 qubits, is disaster. You have to do tomography of 9 qubits. It will take many days, many weeks. But luckily, we are standing on the shoulder of giants from Innsbruck, who came up with this approximate idea that it tells you don't need to do all Pauli's, and if you do sufficient number of them, you can approximate trace of rho squared, and you can only approximate that. And again, it kind of pushing the exponent. This method is going to exponentially fail again, but you push the method, the idea a little further down the road, so we can get this part done and submitted. Anyways, okay. So you add up all these contributions, and this is the histogram coming from them, and you see it's always centered around -1 or less. So good, we do this check. So a little cute thing we could do is to go and braid these particles. So you can, as I said, you make the ground state. It is defect-free, but you can apply X pulses or Z pulses, and you create defects. These defects come in paired, but if you manage to engineer them, one of them could be stuck to the corner, or you can kind of, because it's not on a torus, you can manage to have them coming individually. So don't get panicked if you see one of them and not two. So you create E and M defects. I mean, the name is arbitrary. You call them N and E, M and E. And you say, okay, I'm going to move one around the other. Oh, that's fantastic. You come back and you measure all your stabilizers, all these local parity operators, and you see nothing. Well, it's simply your wave function picked up the global phase. These are Abelian particles, have Abelian statistics. So you get to look at the same object as it looked from the beginning, except it just faded out because it took you many more cycles. So global wave function, how would you read it? Then you remember that you have read Mike and I textbook, which tells you that if you want to read a global wave accumulated during the unitary operation, you can do something called a Hadamard test, meaning bring an ancillary qubit, put it on the equator, and then let that guy pick up the phase. And it does pick up the phase. So you conditionally couple that operator to your unitary, and the phase can be detected at the ancillary qubit, how much it rotated from its original place. Using this standard known fact, you can go and now make a zoology of all these defects and how what is the phase accumulated over when you're braiding them, when you're doing exchange statistics, and versus you do mutual statistics. So you get 0 or pi, they're all Abelian particles, so you don't get anything exceptional. And you can see this is the ancillary qubit, which is outside there, so you get a complicated operation that you have to decompose and do and whatnot, but let's say you get a hold of it, and then you can create E and M. There's another particle called psi, which is a product of E and M, and then you can get any of them that you like to go around any of them, and you make these so-called S and T matrices. Okay, you have said all this to arrive at this point. Good. This is a recent posting, surprise, surprise, with Frank Pullman and his team again. But also I want to say that this is a new mode of doing experimental operation, that we host a student from an external, from a university for a year, and we ask them to bridge between us in this end and the collaborator. I can tell you more about this program, which we call them quantum hardware residency program. So we host a student for an extended period of time of 1 year, and they do the heavy lifting, and behind the scene, Google Quantum AI and my colleagues, we do the calibration, and we facilitate the conversation. Okay, now you remember that Hamiltonian, which had okay, so let's talk about lattice gauge modeling, and then I get to see how is this relation. So in the lattice gauge theories, you want to have fields mediated interaction between matter sites. So this is a very simple lattice gauge gauge theory that you can write on a lattice, and there's a field terms and there's a matter terms, and you can define matter qubits with tau operators on them, and you can have gauge qubits with capital X and capital C acting on it, and you can think about the study this dynamic. But being a lattice gauge means that there is a local symmetry that the Hamiltonian of the system commutes with these local symmetries. And you can take it, so here is the implementing this Hamiltonian might be easy in theory or thinking about it because there is a symmetry and then you can take leverage of that symmetry. But experimentally, actually, is more challenging because you have to be sure your system respects this symmetry all the time. What you could do, you can take advantage of this symmetry and eliminate the matter degree of freedom and arrive at a pure field lattice gauge model, which you can see here, all the taus have been using this relation, all the taus have been filtered out, and now you have only filters. And then, as before, we're going to interpret, we're going to measure AV and BP, and then we can give this interpretation of existing of electric field and magnetic field. Okay, so what do you expect to see this violation again? We're going to do that interpretation. Since 1979, the phase diagram of this Hamiltonian is known by the work of Radking and Schenker. As a function of these two parameters, this was the toric code, this very, very little point that we studied so far was the toric code is that little point, and HM and HE are 0. But then besides that, you get to, and then there's deconfined, the particles are deconfined. And then when you go outside, there will be a confinement. And that's what we are excited to see. Good. So maybe I say very quickly because I'm excited to show the strings and string breaking to you. This Hamiltonian is not exactly solvable, but it's not that difficult to come up with good ansatz which allows you to solve it. So you can parameterize this, the sequence I was showing you before, which took us exactly to the ground state of the Kitaev model, with a parameter called theta. And using a classical computer, you can get to the ground state of, or low energy states of this Hamiltonian by using a classical computer, which tells you what theta angles are good to use. And you can see the results of what classical computer tells you, and also the date dots are the measurements of the energy in the implementation. And you can convince yourself a little bit by looking at these local head and vortex operators. They are not stabilizers anymore. There's no exact solution and whatnot. But you know, it tells you that something is happening and you're realizing distinct ground states. Again, realizing the ground state, although it's not exact, but computationally is not that challenging. The challenge comes when you try to create excitation and when you try to watch them to interact with each other or get scattered from each other. So here is so I remind you of the phase diagram or the behavior in each phase that we're expecting to see. And here, so we make the ground state appropriate for the value of HE and HM given, parameterized by that theta. And then we are going to create a pair of excitation and see what do they do. You see what they do is that in the confined phase, in the deconfined phase, they, as a function of time, the strength of this red color, meaning that where the particles are, it spreads uniformly across the entire grid. In the confined case, you can see that the colors indicate that the particles don't move much. But this is a little, and then here I'm showing you line cuts to the same date, or rather than showing them as a function of time and what happens, more or less showing you something that happens on a decoherence breakdown and all that. That's interesting, but you're noticing they may not be the best choice because you have these particles quantum mechanically, they would just wiggle in their place, and it's just hard to know if they wiggled and there was just a string keeping them together, or they meant to go away. It's not the easiest thing. Here's the imagination. Imagine that there's the Earth and there's a moon, and then all of a sudden you turn off the gravity. They're going to fall apart from each other. Okay, so we are not on that length scale, meaning that we compare the wave function and whatnot. We should really think about it as creating some clever initial states that lead to interference and kind of suppress us to go in certain places and whatnot. So we consider this initial states, which is a superposition of these two configurations. And as I said in the analogy, is like, you have two objects that are rotating around each other, and you want to see if they fly apart because there's no string connecting them, or they stay together because there is a string. And then there you go. You see very clear behavior in these two cases when HM is 0, which is they are deconfined and they just fly apart. That's a vertical axis notion of separation. And the separation being 2 does not change much as a function of time in the case that HM was chosen to be 2. By the way, HE I'm not showing, but is always non-zero. So I'm not cheating because the HE 0 would be against all theories would not like it for this reason. Okay, so we can continue and ask this something along a similar spirit. If I find a particle in here, where is the other particle? So in the confinement case, when I find it here, which is with a probability of 42%, I find it here, where is the other guy? And of course, there's always two guys, right? There's always a pair. And this is where you find them. You can see a very with a very high probability is localized in a given site, meaning that it just doesn't move much around. And here it's just hard to say where it is because it's going all over the place. So the signature of confinement and deconfinement very, very visible in here. They tell you that there is a string, right? The symptotic freedom and all this physics comes that there are two particles that are connected with the strings. And here, we are going to look at this string and then look at the dynamic of the string. What we want to do is to create two excitations, stretch them apart, but then take them out of the dynamic, meaning that they are pinned to the two ends of the chip, to the two ends on these two sides. And then there is a string connecting them because we just generated that. We are going to, this is the correlated we choose to measure to show that the behavior of the string. And we are going to watch this string. If they are confined and whatnot, the string would be tight, it would not move much. But if they are deconfined, the string connecting them are going to have all sorts of wobbly motion from, think about a piano string or violin string. Because piano you're not supposed to see. So you think about a violin string, it's just going to go back and forth. But if it's in the confined sense, you're not going to see it. So here is the example on the confined case that you can see the string where initially at time 0 is in here, and as time goes by, as these SC measurement shows you, it become more or less stay on the top side, never makes it to the bottom side, and more or less stays where it was. Okay. On the deconfined case from get-go, it's not even clear where it is because as you stretch it, it's just there's no notion of where position for the string. It's a very wobbly string, it's everywhere. And then you see you get to later time for this choice of parameter, it's everywhere, essentially. That's what this measurement tells you. And a little dissection of this measurement shows that yes, indeed. So now this is the time, and then I'm showing you I'm showing different slices in time, and then more or less the same physics is shown in here. Maybe I'm just trying to convince you that we are not cherry picking these instances, and the whole thing is a very clear behavior. Yes.
So just to make sure, this is time evolution is given by trotterized circuit.
Yes, I can say that. Yes.
Like I guess probably trotterized enough that behavior to converge.
Trotterized that no, error is about the phenomenon. Evolution under this Hamiltonian with trotter step, which is like 0.2 g, 0.21 over g, is showing you the phenomenon. It's not loyal to the Hamiltonian. The claim is that we can see the physics. Okay. We make the strings, let's break them. That will promise to the last thing. So, vacuum fluctuation could lead to creation of a pair of particles, and the strings could also break and whatnot. And here is the indication of it that we can find in the experiment. So here what you're seeing is that one case we make we create a string and stretch them, and this is the subtracting of the background is shown in here. And see which excitation, and compare it with the case that we did not create the string and say what values you get. So that's AV as in in the absence of any string creation. And then the idea of string is when you create a string and stretch it to the end, and say what are the probability of finding excitations. And you can see substantially the probability of finding a particle on the north side has increased, indicating that there was a string there and possibly. So let me show you another cut to the same data, and that is shown in here, which is for various values of HE. You can see that for this particularly, look at this A1, this particle up there, probability of finding an excitation having a particle on this north part is far more than the other side, meaning that this is just not this is not just an accident, that there's a coherence leading to AV of non-trivial values for AV, but it's actually much higher on the top part, which was string originally existed, compared to the lower part, which is as good as of the background. Okay, and then one little thing in here is, well, maybe that's so much.
I'm confused, sorry. So are you showing the same model in different time scale than the previous slide, or what?
It's yes.
It's just amazing that even if you create string, then of course, if you have gauge matter coupling calculation always occurs and string will break. Is that correct, or?
Yeah, this is a model we study.
Yes.
And gauge has been taken out. There is no gauge symmetry anymore. I eliminated the matter size.
Yes, but physically it's equivalent to the original model. So
yeah.
Okay, so I'm confused. So can string live forever?
Probably not. I don't know. Unless I don't know.
What is the difference between this string vibration slide and the next slide that you have?
No, if we just look at the difference. One case I said, where is my string?
Yes.
Okay, and some case could have been broken, I wouldn't know it. Well, let's just stay to the fact. One case I created this string, and I said, what is this observation? Can I go and measure this at the field size? That's all we did. And it's just the dynamic of the string. And others say, well, what if the string was broken? Can I go and look for particles now? String is doing what a string is doing, but I chose to do these AV measurements here versus what was chosen to be measured here is SCZ. It's just same physics. That's a good question.
Okay.
Same physics. I just look at
the same model, the same time scale, different observation. Yeah, thank you very much.
Okay, well, maybe
So can you measure the string tension and then try to see the area lobe and perimeter lobe? That's the most straightforward demonstration of 5 minutes.
well, it is. You mean like going and bouncing back then? That would be much longer time scales. That's why we just say, okay, we're going to pin them to two edges and just see it vibrates. You need much longer time for them to do the accordion motion.
Yeah, that I agree. But is there any obstruction to doing that, or like
yeah, no, this is
much you can do that, I guess.
No, it just takes much longer time,
okay.
And the system would not survive the coherence.
Oh, okay, I see.
Yeah. We thought about it. Yeah, well, I just want to show who did the work. Well, maybe one more time, and then I can take more questions. Yeah, well, this is the Google Quantum AI team. Who is this is last summer, who do the heavy lifting. But I just want to say that we've been benefited from collaborating with many academic groups. And I'm kind of embarrassed to notice there's no one from Japan in here. So maybe time to change. Well, there is this room. Anyways, okay, I'm done.
Thank you so much. Very nice talk.
Yeah, just one quick question. So, regarding the string, this thing, so what you were measuring seemed like to me was the autocorrelation function of this set of operators.
Yes.
And that's how can be related to, I mean, why I'm confused is that string is a, an extended object, and here you are computing autocorrelation on a given site. So how do the two relate?
You're saying it should be a string of Pauli's. Why is it two sides?
Yeah, I think so. And here it's a single site, I guess, right? Because it's a
Okay, well, it's a single side. Yeah.
So I mean, just a bit confused. Just wanted to ask.
Yeah, I don't know. I think it is maybe zeroth order signature because the way you stretch it originally, this correlator goes non-zero at this one, and you just keep tracing that thing. But
I guess you could imagine measuring like a hoofdloop, right? As a more direct signature.
yeah,
I would think, but I mean, yeah.
no, I think probably it just would not be as survived so easily.
I have two technical questions. The first is due to error mitigation, and the second is the controlled time evolution. How expensive is that versus the original application?
So we do error mitigation, and every experiment I show had its own zoology of error mitigation, starting from reading IPM papers of what do they show. So we go through the whole thing. I'm not in the supplement to describe which one we put at the end. The second question is
The control time evolution for the Hadamard test to get the global phase.
right.
How expensive is that?
It is actually expensive, and it was rely on it is becoming now local, and it was rely on having it nearby and whatnot, but it gets very deep. If we could not do it, you see these operations, it has to be decomposed further, and it's not easy. Yeah.
Set angle, can we include it and then do the similar thing?
Take time there.
Set angle, yes, like a EP.D. Yeah, people have the implementation of the lattice at least. That's something I know, and then you can try to at least for many reasons.
So it would be U1 gauge here.
Yeah, you will consider with the set angle, especially set equal pi. I'm been fascinated. So
yeah, I think it's a little more challenging. For now, we just focus on showing the phenomenology of how much you can go with just this simple model. But it's a Z2 for now, but yeah, that would be much more challenging.
Can you do U1 gauge or C2 or whatever?
But I mean, any gauge you tell me would be translated into a sequence of C0 and C0 gates and individual qubit rotations, and we just have to see how demanding it gets. Yeah, I mean, I'm not showing any layers of gate, but you can imagine there's 700 or so of entangling gates and whatnot that's been applied for the whole thing, and it's not.
No, it's not the problem of qubits, but problem about the gates.
We have to be very clever with choice of gates, so this compresses and compiles in a very effective way. I mean, the gates are maybe 2 9 close to 3 9s, but you put 100 of them together, or a few hundred, it's just not going to survive easily.
Comments, it's now or never because Pedram will be leaving. So, if not, I think a good moment to stop the morning session. Thank you once again for your contribution, both speakers.